In the previous video, we went over the differentiator and we saw that we had some issues, especially at high frequencies. We had something like a noise amplifier. In this activity, in this video, we are going to solve that issue, change the circuit a little bit, as well as go over the first order high-pass filter, active high-pass filter. So let's start with the integrator that we were working with. If you recall, the main issue that we had with the circuit was that at high frequencies, the capacitor becomes a short. And so we have an inverting amplifier configuration where the output is minus RF, the resistance in the feedback, over Ri, and Ri here, the resistance, is 0. And so we have very high gain as the frequency goes up. And so if you have high frequency noise, you will be amplifying that. How do we solve that? Well, we just want to make sure that when the impedance of the capacitor is 0, you have a short there, you still have an RF over Ri ratio that we used to have in the inverting amplifier. So we can do this, for instance, Ri. So with that, we have a skeleton to work with. Let's do a qualitative analysis of this circuit. As in previous videos, from now on, I'm going to recommend that before you start doing any math and writing any equations, you just do a sanity check and see if you qualitatively you can see and find out what the behavior of the circuit is going to be. So for frequency selective filters or circuits, you want to make sure that you check at least at omega equals 0 and at omega equals infinity. At omega equals 0, the capacitor is open. Why is that? Because we have the impedance is 1 over j omega c, omega is 0, 1 over infinity, 1 over 0, tends to infinity. So if we have an open there, what happens to the output? Let's see. Here we have this disconnected, and we still have that. We have a negative feedback? Yes. The output is going to get adjusted so that the inverting input equals the non-inverting, which is 0, so the output is equal to 0 at low frequencies. Output equals 0. What about high frequencies? At high frequencies, the capacitor is a short. And before, that created a problem for us because we have very large gain. But now, what we get at those frequencies, if this is just a short, we have our inverting amplifier. What is the output? Minus RF over Ri times the input. Great. So what do we expect in terms of a frequency response? At some high frequency, this is going to have the gain of minus RF over Ri. At 0, it's going to have a gain of 0. So something like that is what we expect. We are dealing here with a high-pass filter. Now, if you recall, the ideal differentiator, the frequency response, looked like this. And that's where we had high amplification at high frequencies, where we have noise, and that created a problem. And so, how is a first-order active filter different from a differentiator? And over what region it behaves the same? Clearly, not in this region here. where we just have a circuit that behaves as an inverting amplifier. It is this region. So if this is going to be our cutoff frequency, is for frequencies that are less than the cutoff frequency where we can match the characteristics of a differentiator. With that, let's do the actual mathematical analysis now. Going to analyze the circuit in the S domain. We have already analyzed the circuit for any generalized impedance with the inverting configuration, where this is C input and this is the negative feedback. All the circuits that we did earlier with resistive networks, the results are the same once you're working with impedances. So what do we know? That the transfer function h of s for this circuit is minus fc over fi, and we have analyzed that before in previous videos. And so fc in this case is rf minus, and the input impedance here is Ri plus the impedance of the capacitor, which is 1 over Sc. So that's it, but typically we want to put these circuits in a standard form, meaning we want to do the standard form for a high-pass filter that is active is K S S plus omega C, where omega C is the cutoff frequency. And so let's do some algebraic manipulations, and what we get here is minus, why don't we divide everything by Ri, and we get Rf over Ri. Ri over Ri is 1 plus 1 over S Ri times C. And we are going to multiply now numerator and denominator times S. And so what do we get? Minus Rf over Ri S plus S, and S is going to cancel, so you get 1 over Ric. And with that we have a transfer function. We also find that the cutoff frequency is 1 over Ric, or the frequency is 1 over 2 pi Ric in hertz. Remember that since we have a transfer function, we can find the output for any input. The output in the S domain is equal to the transfer function multiplies times the Laplace transform of the input. Again, this applies not only for sinusoidal inputs, but for any input that you want. You can see how this will react to a step response or any other input for which you can find the Laplace transform. And the output is the inverse Laplace transform in the time domain of the output in the S domain. Now we can also do the frequency response by evaluating the transfer function for S equal j omega. And so we get minus Rf over Ri j omega plus 1 over Ri times C. You can leave it like this, You plug in an omega and you get the frequency response. You get basically what the gain will be at that frequency and also the phase for any one of them. Now, you can also plot it as a function of the frequency, and you get a plot of the frequency response. Let me just do the magnitude here. The magnitude will be minus Rf over Ri omega, and here it is the square root of omega squared plus 1 over Rc squared. Now notice that for omega equals 0, if we plug in a 0 here, 0, what do we get? 1 over Rc, this will be 0, 0, and it will get 0. And for high omegas, this is going to just go to minus Rf over Ri, right? Okay, so let's actually do a plot, at least of the magnitude response. So we see that for omega equals 0, this is 0, right here, okay? And for omega, as omega, this effectively is what we are getting, right? It goes up. And then we are at that gain, minus Rf over Ri. You need to put it in decibels. This is 20 dBs per decade. And the corner frequency here, if I put this in frequency in hertz, this will be Fc equals 1 over 2 pi Rc, as we expected. Now, one thing to keep in mind is that the first order active high-pass filter only is going to behave as an integrator over this range, over this frequency range here. In this other range is an inverting amplifier. As we can see, it's a it's a high-pass filter because high frequencies go through and they get amplified, and low frequencies get attenuated. Okay. Now, this is in dBs, so if this is Fc, 1 decade before 0.1 Fc, this went down 20 dBs, or 1 over 10. Thank you.